mutation, and as I alluded to, how we can take different types of cancer genome variation, not just at the microscopic level, but really at the molecular level. This is actually a quote from my postdoc supervisor, Matthew Merritt. He loved this example of really all happy cells are like each unhappy cell is actually unhappy in its own way. So this is actually a plot from circles.ca. This is actually Martin Stravinsky's site from the BC Cancer Agency. This is actually not showing a cancer genome. This is actually showing all the ways that a genome can or could be modified. And these arcs are actually showing regions of the genome that are related to each other, have a similar sequence. If you zoom in here just onto this one little segment, each of these tracks refers to one of the different ways a cancer genome or genome can be different from another. Point mutations are the most famous, single base pair changes. Copy number alterations, really wholesale changes of thousands, hundred thousands, or millions of bases of the genome being gained or lost. Structure rearrangements, taking a piece from one chromosome, attaching it to another. Of course, within all of these are the genes and the elements that regulate them, regulatory elements, pathways that those genes encode, and there's a lot of redundancy in the human genome. These homologous sequences, these epigenetic modifications, really layer upon layer of regulatory control on top of the sequence itself. The other lesson with cancer is you don't sort of get this boom of massive aneuploidy or copy number or mutational changes at once, but rather cancer is actually thought to sort of accumulate mutations over time, and really it's not until the acquisition of a driver mutation where really you start, where things really start to take off, where you start to get this highly unstable genome, highly unstable cell, that then is prone to acquiring additional mutations such as copy number alterations, and some of that's actually being driven by therapy itself. Only this model is just completely by abstract. It really is the number of mutations accumulate over time until you acquire what have now been termed drivers. Really, still one of the central challenges in cancer genome research is to differentiate a driver mutation from the inevitable passenger mutations that accumulate over time but are not thought to have biological function. I mentioned external forces like drug treatment can select for specific clones. I just have a slide later on about this idea of clonal selection within a complex cell population. But before I got there, I want to talk a little bit about mutation burden, this idea of the number of mutations in each cell. And really, in this analysis here from Broad Institute, just looking at the number of mutations across all cancer types, and the general trend being that pediatric cancers, hematological malignancies being relatively low mutation rate, the cancers associated with environmental exposure, smoking, sun exposure have a higher mutation rate. I'm not so sure about hamburgers, but in general, higher mutation rates on the right-hand side of the slide. But really, it's not a hard and fast rule. At the population level, yes, these cancer types have low mutation rates, but I've sort of highlighted two sort of anecdotal exceptions to the rule. Neuroblastomas is actually from work I did while I was a postdoc there. That's sort of a mysterious case with an amazing number of mutations, actually just as many mutations as a late-stage lung cancer. This was actually a child with neuroblastoma. In this case, they were the only patient with 2 hits in the DNA repair gene. They had a mutation, one copy of the MLH1 and a deletion of the other copy. This cancer cell had lost its ability to repair its DNA. So in this case, we had a nice molecular reason for what would be expected to be a low mutation rate cancer to have a very, very high mutation rate. The exact opposite story here in melanoma. This is actually the only melanoma in that study that did not have sun exposure. It's actually a tumor on the bottom of the patient's foot. Just extraordinarily bad luck. They had cancer of the same cell of origin as other traditional melanomas. But again, very different at the molecular level. Even though down the microscope, the cells look like melanoma. It's really level. This is a very famous slide. It's been updated actually several times. Really, this idea of hallmarks of cancer. Really, the idea to take these biological themes or biological processes that are active in cancer and assign them into relatively few distinct characteristics. So this circle has actually grown quite a bit since the original Hanahan and Weinberg hallmarks of cancer paper. But really, this idea of tumor cells acquiring abnormal activities using pathways that are already active in normal cells. So really, this idea of cancer being dysregulation of normal cell processes and often turning on pathways in a cell that they otherwise should not be active in, driving sustained electrical signaling, evading growth suppressors, etc., etc. Really, this idea of just reusing pathways that already exist. This idea that oncogenic somatic mutations target a core set of biological functions, and you'll hear me use a couple of terms, this idea of driver mutations or oncogenes. These are really thought to be sort of the activating mutations, really the mutations, copy number alterations, rearrangements that drive or activate pathways that shouldn't be expressed. And the other category being tumor suppressor genes. These are sort of the cell's brakes. These are trying to be turning off pathways, and these are the genes that are commonly deleted or have loss of function mutations. And the whole point of next-gen sequencing is you will read out all of these classes of cancer genome variation that then result in a cancer phenotype. And this is really still a challenge, especially in these tumors like melanoma, lung cancer. These tumors have thousands of mutations, and the real challenge is to hone in on specifically what are the mutations that drive these tumors, and to treat patients, what can we do about those? How do we actually act upon the knowledge of activated drivers and loss of tumor suppressors? So that sort of brings me to sort of the area I like to work on a daily basis, which is how do we use targeted therapies, immunotherapies, to bring those to bear on specific tumor types. I've shown 2 of the most famous examples. In this case, these are the example of lung adenocarcinoma with an activating mutation of the epidermal growth factor receptor, so a mutation, a receptor very high up on a signaling pathway that activates the entire pathway. Sort of the canonical personalized medicine principle has really been this idea that inhibiting this pathway shrinks tumors that have these precise mutations. Same sort of story here, metastatic melanoma with activating mutations of BRAF. You can just see by eye. Really, this poor patient here has covered in metastatic melanoma, and really these very, very dramatic responses, specifically with a BRAF inhibitor, that really hits a lot of those tumors really hits all of those tumors in a targeted way. The real challenge here is that resistance to these inhibitors inevitably arises. In almost every case, especially with these targeted therapies, you'll often see these dramatic responses, but then some sort of resistance mechanism will arise because these tumors have such plastic genomes. There's either a subclone that already has that resistance mechanism, or you've really selected using drugs for a specific cell that has a resistance phenotype. This idea of linking drugs to genomes is really is still a very, very active area of research. This is a paper where Chris Sanders' group took basically all the tumor genomes in the Cancer Genome Atlas at the time, picked out relatively few genes that have been linked to pathways, and what they found is that you really don't want to look at these genes in a single way. 12 of those genes were actually being hit not just by point mutation, not just by copy number alteration, really this idea of genes being hit in multiple different ways using multiple different types of cancer genome variation, but having the same phenotypic effect, activation or loss of tumor suppressor or cancer driver. The other big lesson from this study, so the way to read this, each column is a cancer type, Each row is a gene, and they've drawn a little pathway diagram down here to sort of group these genes into themes. So the lessons from the study, lesson number 1 was druggable alterations cut across cancer types. In this case, FGFR activation happens in bladder and 2 other cancers as well. So really this idea of one drug, one cancer type, really starting to fall away as you get this high-resolution view of the cancer genome. Combination therapies may be effective, and actually no longer may. They are effective in tumors with compound pathway alterations. So in this case, these cancer types that have activation of both the PIK3CA-AKT pathway and the CDK and the CDK pathway, really these idea of coincident mutations hitting 2 pathways at the same time, so there's potential for combination clinical trials. And the other lesson that at least half of the tumors have at least 2 destructive druggable pathways. So they're called, in this paper, was really for, let's think about combination therapies rather than trying to hit these pathways one by one, or we do inevitably see resistance to single agents. The other compounding factor, not only are these tumors these tumor cells hit in multiple ways, they then spin off progeny, and these progeny then go on to evolve in their own way, and actually result in tumor masses like this, where you have a blue cancer cell that has then perhaps given rise to a red subclone and a yellow subclone. You can actually see these microscopically, maybe not so great here with the light, but really what's happened here is you now have cells that inherit the cancer genome alterations from the parental cells, but then go on to acquire their own resistance mutations or their own oncogenic drivers. So even if you have a therapy that's very effective against the blue clone, there's potential that the red and yellow clone may still persist. And there's a need to monitor and overcome the drivers that are active in those subclones as well. Actually, a nicer diagram of this published 6 years ago now is really this idea of starting with your tumor clone, the acquisition of multiple clones over time. So each of these clones is defined by different cancer genome alterations. You might have a yellow mutation here, might have an orange copy number alteration here, might have a rearrangement here in purple. The idea that then you have chemotherapy acting on all of these clones at once, and the risk that a resistant clone may be somewhere in that larger cellular population that may then persist and then have a space into which can then grow and additional cancer genome alterations. So the real challenge here to not just look at cancer genomes at one point in time, but really having the ability to sample multiple tumor samples of the actual tumor tissue, or allude to later a little bit of work in cell-free DNA sequencing, really trying to read these subclonal populations and resistance mechanisms out more routinely, rather than trying to rely on diagnostic material from 4 or 5 years prior. The other challenge is these tumors will also change and evolve as they move throughout the body, as they metastasize. So in this case, some work by Peter Campbell in the UK, really starting with a primary tumor and then seeing metastatic masses that then, just like in clonal evolution, start to acquire additional cancer genome alterations. We have this primary tumor, spins out a second metastasis, spins out a tertiary metastasis. And this is really where clinical interpretation is extraordinarily challenging. First of all, how do we sample all of these metastases? That would be the main maybe one to get there. But also, what do we do about them? Do we have to treat this net, or is there some clonal truncal mutation that you could really hit that could blow away all of these nets? Certainly in the BRAF mutation example I showed you, that was very effective. You do see these dramatic responses, but then you also see these dramatic resistances as well. So why do next-generation sequencing, or why do molecular testing for cancer in general? Obviously, treatment, you want to see what are the genome alterations, what targeted therapies may work. Are you already resistant to a drug? Are there specific drugs that you cannot metabolize? Drug resistance and metabolism. I'll talk a little bit later on about an inherited hereditary cancer syndromes, really where you're born already with a loss-of-function mutation of a tumor suppressor, really with a very, very high predisposition to cancer. It's very early onset cancers in these patients specifically. And part of what kind of cancer do you have? Even if there's not a goal to assign a patient to a targeted therapy, what we've seen with increasing number of tumors being sequenced and analyzed is that there are multiple molecular subtypes even within breast cancer, lung cancer, brain cancer, virtually all cancers. There are distinct molecular subtypes, some of which do better clinically than others. So I'll just pause here quickly. I don't know if anyone has about sort of the overview of cancer genomics in general before I dive into a little more of the I guess, N of 1 single patient analysis. Okay, so the first part of the talk is sort of that overview. Here's what the landscape of cancer genomics looks like. Really how the four general happen. You extract genomic DNA and RNA, a cell, biopsy, blood, cell-free DNA, some sort of extraction. You make a library. A library is essentially DNA that's been made compatible with a machine that can read DNA. So basically you take this DNA, in the case of Illumina sequencing, which I'm almost going to be showing exclusively, you put little adapters on either end that are unique to that machine. You then load that DNA onto the machine, like an Illumina sequencing device. That generates a huge text file of A's, T's, and G's. And this is really where things are much less standardized. Sort of the more and more custom you get, the less standardized it becomes. The alignment is very standardized. And as you get down to how to interpret a genome, that's really more lab specific. But essentially those are really the four steps. Extract DNA, make libraries, put them on a machine, then analyze the data. I mentioned a big text file. This is literally I run from a project that I was running. Essentially, each of these is a DNA sequencing read, 75 base pairs, and this is 25 reads on a single Illumina HiSeq, so conventional machine. One lane of an 8-lane flow cell generates 600 million of these, so you get millions and millions of A's, T's, and G's. And the first step is to compare them to something. What do any of these mean? No one wants to look through 600 millions of these. That's where this idea of a bioinformatics pipeline comes in. It's really exactly like an oil pipeline. You want to have your text file at the beginning. You want to run it through a series of software modules, akin to sort of a pipe module. But essentially, you want to run all these software programs in a systematic way, end to end, to go from raw DNA sequencing, a raw DNA sequence to a list of variants at the end. Building one of these also very much like an oil pipeline. You want to really run through a series of software that are all compatible with each other. You want these softwares to really link up end to end without leaks. And you want to put them together in a really systematic way. And I'll have a slide based on each of these steps. Really, the idea of taking the first sort of that text file, align it to something, some sort of reference. In this case, we use a human genome reference sequence. Anyone can download this off the internet. I, of course, have a copy on my laptop, and you probably will by the end of this workshop as well. Pre-processing, really sort of cleaning up that alignment in areas that are very difficult to align. I'll show you an example of that. QC metrics. Did all your reads align to human? Did you do a human Do you have a bunch of other sequences that are not necessarily human? Did the experiment work? Does it look like the cancer that you were studying? Variant calling out mutations, translocations, copy number alterations. And I've just put in slightly, basically grayed out the bottom. How do we interpret these variants? How do we write some of our report to communicate this analysis to clinicians who may act on it? Really, the go-to place for almost every, and certainly I've worked on, is some modification of the genome analysis toolkit best practices. And this is basically a more technical version of the slide. Really be going from raw reads, going through an alignment, going through some cleanup of that alignment, some variant calling, and then tidying up those variant calls. So this is actually described in great detail on the Broad Institute's website. Another great tool just to bring on your attention to is the CARD suite of tools, which is really a collection of QC tools that really look at the output of this pipeline and allow you to compare it across runs. This best practices work actually came out of a lot of the non-cancer work being done really across the world. And for cancer genomes, we've inevitably had to modify this to bring in our own cancer-specific callers. some very challenging things that take tools that were written specifically for germline analysis and apply those specifically to cancer. I just listed some of the tools here for doing variant calling specifically for cancer, and then also the types of cancer genome variation that we're looking at in cancer that may not be certainly as frequent in germline or normal cell genomes. So this is really step one. This basically, if you took that big text file I showed earlier, aligned all those reads to the human genome reference, this is really what you get. This is a software called Integrated Genomic Viewer. I think there's a little tutorial session specifically on how to use this tool. I'll show you a lot of screenshots of how this works, or how to read these screenshots. But just to orient you, the chromosome is here on the top. So just like the chromosomes I showed you earlier, they've taken that little banded diagram and put it horizontally along the top. So we're looking at this portion of this chromosome. In this case, we're only looking at 92 base pairs at a time. In white is the human genome reference sequence, and then gray is a histogram of the number of reads assigned to each base. These are all the sequencing reads. This is the data I showed you on that slide earlier, and you can see that data represented in this way is a lot more human readable than it was just in the flat text format. First of all these reads have more or less the same sequence, and chosen a region that doesn't have any variation. So in this case, all these regions basically match perfectly with the human genome reference, and now we want to run callers that look for differences between our data and the reference. And there's actually a Wikipedia article called Short Read Sequence Alignment. There are many, many ways to do alignments. BDFA is the one I've used here, but there are many, many others. So really you want to choose a specific aligner appropriate to your biological question. This is a cartoon of the exact type of data I just showed you. So the human genome reference being here along the top. Here's chromosome 1, chromosome 5. Here are all the sequencing reads, and here are the types of genome variation we want to find using bioinformatics. Point mutation, single mutation difference from the reference, an indel, an insertion or deletion of a base, multiple bases in a small region. Missing DNA, so tumor suppressors in regions that don't have any reads whatsoever. If you don't put DNA into your sequencing device, you're not going to get reads out. That region is not represented. That looks like a deletion. A hemizygous deletion, so one of the two chromosomes is deleted. That means you get half as much data as you'd expect. A copy number gain, some of these oncogenes get amplified tens or hundreds of times. As a result, you get tens or hundreds of DNA sequencing reads mapping to that region. And translocation breakpoint, where you take one piece of one gene, attach it to another piece of another gene, and this now has brought one gene under regulation, under the bench for gene chromosome 1. So these are very powerful oncogenic drivers in cancer. I'm not going to talk too much about pathogenic sequences, but really not everything aligns to the human genome sequence, especially in cancers like cervical cancer, for example, where one of the original drivers of those cancers is exposure to virus, HPV, EBV, etc. In this case, those reads, of course, come through in your DNA sequencing reads, and you can align those to other references on the human genome reference. And here's sort of a cheat sheet of sort of the ways that we can think about and sequence DNA and start to infer the presence of proteins that DNA is wrapped around. Whole genome sequencing, this is put all the DNA into the sequencing device and sequence whole genome sequencing. Exome, this is focusing specifically on exons, so only the coding portions of these genes. Much, much cheaper. This is about 1%, looking at 1% of the genome relative to the whole genome. Targeted gene sequencing, this is what we often will use in clinical labs. Much smaller targeted panels, much more cost-effective, much easier to interpret. Targeted variant gene typing, this is getting even more focused, looking at single bases, single mutation. Very high throughput, very inexpensive, the least comprehensive test, but certainly the most clinically actionable. And epigenome modifications, really looking at methylated promoters or other regulatory regions. RNA sequencing, looking at the functional output of DNA, looking at transcriptome sequencing, either looking at whole RNA sequencing. Targeted RNA sequencing is also a protocol that's being increasingly used in clinical labs. And microRNA sequencing, looking specifically at small microRNAs that are essentially confer regulatory control on gene expression. And I'm not really going to talk at all about protein mapping or DNA fingerprint mapping. Actually, be an entire bioinformatics workshop on this topic specifically. I want to show you real data as often as possible. So here's the exact same sample sequence in genome sequencing, exome sequencing, and RNA sequencing, focused on a very important cancer gene, KRAS. The way to read this, so here's the region for 9 kb region, so we're zoomed out quite a bit further than we were on the previous slide. Here's KRAS down here on the bottom, so exon 1 down at this end, so the minor strand going from right to left. Whole genome sequencing, you just get a sea of reads, so all those gray sequencing reads I showed you earlier, each of those just shows up as just a little tick on this display because we're zoomed so far out. Exome sequencing, we've essentially used a reagent that will allow us to only focus our sequencing reads on the exons of interest. This is where the coding mutations live. This really is much more cost effective because you don't have to look at the reads and intervening regions that you may be interested in if your question is specifically around coding sequences. And RNA sequencing, you let the cell do the exonic selection for you. So in this case, the cell spliced out the intron, so all of your reads are only mapped to exons as they should be. You also get the added information of what exons are attached to which exons, and this is also quantitative. So if you have very, very high coverage of specific genes, those genes are expressed at a higher level than genes that have low coverage are expressed at a low level. I use the phrase whole exome and whole genome sequencing. That's really a bit of a misnomer. They really don't actually measure anything, or probably more specifically, we don't have great bioinformatic methods to assign absolutely every single sequencing read uniquely to a region of the human genome. This is actually a slide from my own work in neuroblastoma. In this case, little tiny slice here is a neuroblastoma tumor. And the y-axis here is a single exon. Each little slice going this way is an exon. One means that we are completely confident in where those reads were aligned and our ability to find mutations in those exons. And so these are the regions where we have no doubt we can find mutations, we have good coverage, we're well powered. As you get towards the bottom of this plot, you can see our confidence in finding mutations essentially drops to zero, not just in the exome sequences, which are in these purple, but also in the whole genome sequences as well. This is really sort of a blind spot in the genome where they're highly repetitive, our reads are short, we just cannot be confident that in our ability to find mutations necessarily in this region. The other interesting technical aspect is that the blind spots in the genome are often, down here they're essentially the same as exome sequencing, but often they're actually not exactly the same as exome sequencing. This is due to differences in read length, mappability, and just the sheer depth of sequencing. With exome sequencing, since you are able to focus the capacity of your DNA sequencer on a relatively smaller genomic footprint, you can now sequence those regions to much deeper coverage and have much greater confidence in the mutation calls at each of those bases. So I still use the terms whole genome and whole exome sequencing because the concept is you are really trying to be as comprehensive as possible, but it does not necessarily mean 100% of the genome or exome sequences.
On the whole exome, what would you say percentage of exome?
So I think at the time it was about 80% of the whole exome was covered at, in this case it was only 14 exons needed to be called covered. I think that number has probably gone up to 90 plus now. But I think there's still a lot of room for a lot of sort of custom panels to look, especially at these hard to read regions, and to complement not just Illumina sequencing with other sequencing technologies, longer read sequencing technologies that basically generate much larger reads that are much easier to map across these hard to capture and sequence regions.
You mentioned earlier and so
I have one slide on PacBio. I'm not going to cover those technologies in great depth actually in this talk. Yeah, rarely. I don't really know of any clinical labs who are currently using those technologies due to problems specifically with background error rate. In clinical labs especially, we're quite focused on point mutation detection. Those technologies have very high background point mutation error rate. I think they are going to find a place at some point of resolving large structural variation, but they really need to compete on not just sequence quality, but also cost as well. Certainly dollar per base, it's very hard today to be telomerase sequencing. So that's the data that's by far the most ubiquitous. I wanted to just give some context to what RNA sequencing data looks like. This is actually a plot I like to make for all of our RNA sequencing data sets. So for a single patient, I like to just plot all of the exons and just say what is the expression level for all those exons, just to sort of get a feel for what's the dynamic range of our data. I actually do this for almost every data set I get. Before I really do anything, I make a distribution, I look at what is the shape of the data. And I show it in this case because this is actually data from a breast cancer patient, and we want to know what type of breast cancer are they? Are they ER positive? Are they PR positive? What specific markers are they expressing, and at what level? And what we want to do is take the single patient, really just compare it to two reference sets: the tumor from an ER positive breast cancer and ER negative breast cancer. The colors are really not showing up great here. In this case, here's the ER right here in red. Here's the ER transcript, and you can see the corresponding transcripts down here in the ER negative breast cancer are really quite low. They're really well below the threshold here. And the patient as well, basically what we want to do is look at, I can't even see it, the story here, we essentially want to take these reference genes, look at their level in the patient, and basically compare those to reference sets as well. So if these dots are higher up in the patient and corresponding to a specific threshold in a training set of ER positive breast cancer or ER negative. The third type of cancer genome variation probably being used more and more, being read out more and more by next-gen sequencing is epigenetic modification. In this case, this is another IGV screenshot. I've shown MLH1 here along the bottom. Here's the promoter that controls this gene, and in this region, methylation of this promoter has very strong control over expression of that gene. So in this case, here's normal tissue. This promoter is unmethylated, and this actually results in normal expression of MLH1 in normal tissue. And here's the exact same type of data, the exact same assay run on endometrial carcinoma, and you can see the promoter has essentially turned completely red. So what's been done in this experiment is they've taken the DNA, they've treated it with bisulfite, and that converts all of the unprotected C's into a T. So this is into a T, and this is really indicative of essentially a promoter with a whole series of C's in the CpG island are unmethylated, and therefore result in normal expression, normal tissue, but silencing of this gene in cancer. Just like mutation calling, this assay is completely quantitative as well. So you can see this promoter is methylated in this tumor, but you can actually see a sort of a shadow of blue signal as well. And this is still persisting from normal cells that are also present in the same tumor tissue. Sort of a cheat sheet, great for sort of exams, sort of coming up with an experimental design. Really, none of these assays really stand completely alone. Genome sequencing is great for sequence mutations, copy number alterations, etc. I won't have to go through this in great detail. But really think about having to not just read out these sources of cancer genome variation in one shot, but really start to think about integration of these types of mutations. So a experimental design I'll use quite frequently is actually a combination of both exome and RNA sequencing. Exome to get the sort of the parts list, what are the mutations, what are the copy number alterations. I'm going to talk a little bit more about purity and ploidy, how do we sort of challenges in working with clinical samples. But not only what are the mutations, but what ones are actually expressed, which ones are actually being used by the cell, which ones result in loss of function or loss of expression of a certain gene, which mutations are expressed at a very, very high level. Methyl-seq as well being very useful for looking at regions or genome variation that can result in loss of gene expression, but you're completely blind to using exome sequencing. So I'm going to go through this list sort of one by one. So the next sort of series of the talk is really just march